AlbertaLoop will be presenting essentially kind of our future plans and goals for Hyperloop and kind of how we're tying it into the business/economic aspect of things. So first things first, we're going to be analyzing, the differences between high-speed rail and Hyperloop. And from kind of an economics point of view, the two are pretty interchangeable because they fill the same demand and niche market. So, if I say high-speed rail and I say Hyperloop, I kind of mean them interchangeably. And both have their advantages and disadvantages for certain applications. So what's one thing that sucks about Hyperloop and high-speed rail? It's hella expensive. We all have no money and we're all poor. So how do we justify this and how do we justify constructing it? Well, you have to do an economic analysis, which is everyone's favorite thing. So first things first, we need to understand how demand is distributed along a curve. A lot of folks will assume that demand is linear, when in reality, it actually follows something like an S-curve. And that's derived from your standard deviation, which, that's derived from your normal distribution. So when you're starting out here, there's not going to be a lot of demand for your product because, not many people know about it. People have no confidence in it, whatever. And then as more people find out, the usage of it or the demand for it will increase exponentially up until you start to get to around 50% level, whereby they'll start leveling off and approach an asymptote like 95% load factor or demand, because there'll be always some holdout or some amount of personnel who will not transition into whatever you're offering. And now the second thing it's important to understand with Hyperloop and high-speed rail is that there are substitutes for it. And what substitutes mean in an economic point of view is there are alternative modes of transportation. So that can mean driving your car, that can mean flying an airplane, that can mean taking a different train line if that's available. So in order to understand, how good of a substitute it is or how interchangeable people see it in their minds, you have to actually look at demand elasticity for that product. And what that essentially means is, if you have a Mars bar and a Kit Kat bar, most people will be pretty damn impartial to which one they get. So, you'd say that's almost perfectly they're almost perfect substitutes, meaning that, they don't really care one or the other. Whereas something that's, an imperfect substitute or not a substitute would be like water and a graphics card. People will have to choose water because they need it to survive, but they don't need a graphics card, so they will not choose a graphics card if they have to choose between one or the other. And, in this case, they're perfectly inelastic and they have no correlation between each other. And why this matters is because once we move into modeling, a high-speed rail network or a train network in relation to other modes of transportation, for example, driving, we can see that there's actually a pretty unique distribution, not distribution, it's a pretty unique topology in terms of demand given certain market factors. So the ones we chose to account for was fuel pricing and ticket pricing for, a range of prices and its impact on overall demand given an elasticity of 0.5, which is going to have to be verified, or we're going to have to conduct more research and surveys to verify, and a demand curve that's S-shaped. And this is kind of what we found. So if you notice here that as you lower ticket pricing and increase fuel pricing, demand for high-speed rail increases. And now, what does this actually mean? Because I don't know half the time. And how do we actually come to a meaningful conclusion from this? Well, we do what is called a Monte Carlo simulation. So using some stochastic math, we can actually simulate diesel prices or fuel prices into the future. And I just chose to use diesel prices because it's the most applicable for most vehicles. If you want to convert this to regular, petrol pricing, you just add about 20 cents. And as you can see here, over the next 5 years, we're expecting diesel prices to rise from an average of $1.89 per liter up to $2.50 per liter. And we're doing the same thing for electricity prices. We're expecting electricity prices to fall from an average of about 12.3 cents per kilowatt hour to about 9.13 cents per kilowatt hour. So if we apply this to our demand curve, we can see that, in the realm of fuel pricing, if we go along this line and take the second order derivative, we'll find that in order to be most unitary, in order to have the highest unitary efficiency for ticket pricing or for, an output, we need to have our ticket pricing at around $60 to $70 a ticket. And if it's at $60, $70 a ticket, that actually brings it in line with current alternatives that are available for this 300-kilometer long route, which we selected, and that was specifically the Edmonton to Calgary corridor. So this actually kind of verifies our estimations for demand curves. And now, how do we arrive at this? Well, where's the engineering, and how do we actually get to the $60 price ticket or pricing? Well, we start out with
me. So I will talk about our engineering sort of portion. If you can hear me.
I can hear you.
Perfect. So yeah, so I'm going to first sort of talk about our software, where, as you can see, safety is going to be our #1 priority. Our sort of goal with our electronics right now is to make everything as effective, like performance efficient as possible to reduce costs. We also want to make sure we're monitoring our system properly. And this is our software side. We plan on controlling and monitoring our system from wireless connection, which is going to be TCP. And we'll be implementing our own protocols and safety protocols to better understand what's going on with our system. This will be packaged in our electronics. Which is our next slide, which is going to be our sort of PCP dependent modules. We have 2 management modules, which will be our battery and cooling management systems. And we will have controls, which will be our navigation, brakes, wireless, and motor controls. And this will help ensure that we are always knowing what's going on with our pod, and we're always can be safe with it. This is all controlled in our onboarding control system. We're currently using TNC microcontrollers, but we will switch to PCB relatively soon. We're also using a CAN bus protocol. It's standard and it's the best and easiest to use. Everything you see in the right diagram is controlled by our main control board, and it'll be back and forth. It is in our main control board, which we will have our state machine, which is our next slide, and it will be our interface between our wireless network and our CAN bus. This will where we will be taking in commands and sort of setting our state and recording the state that we are in so we know what's going on with our pod. This will utilize a ChibiOS. And one important thing to note about our state graph is that no matter what state we are in, we will always be able to go back to our fault and e-brake. This is important because we don't want a disaster to happen. We don't want anything bad to happen, like lose control. Even if we say lose wireless connection from our control center, the system will automatically default back to the e-brake and fault. The state machine is controlling all of our modules, which we'll look at first, our navigation control. In here, we have a temporary GPS module because we are not in a vacuum tube, so we need to keep track of where everything is. We also have an accelerometer, gyroscope, Hall effect sensors, and a tachometer to monitor our speed, position, distance, and just sort of understand where our pod is and how it's moving. We are also utilizing a Kalman filter, which basically takes a weighted average of our past state and our predicted state of what we believe is going to happen. And this will help us better understand variables we might not be able to observe normally. Just take all the things we see and better bring up an estimate of what we actually want to do, what we're seeing. In our brake control, this is important. We're using currently solenoid valves, and we have 2 sort of braking mechanisms, an emergency braking and a regenerative braking. Emergency is obvious for stopping when we need to, and we have the regenerative because it's more cost efficient and will help keep the batteries longer life and reduce the amount of times you will need to charge them. Currently in our design, we have rotary motor braking. So this is very easy to add regenerative braking to, but we will in the future add linear induction motor, and we will make these regenerative as well. And these will help save costs and reduce costs for our overall process. Speaking about batteries, we have our battery management system. Currently, we're using a Runnegi smart lithium iron phosphate battery. There's sort of two sides to it. There's a 48 for our medium power, our rotary motors, and then 12 volts for the low power electronics, our PCB, TNCs, all of those. This BMS will manage our cell charge and battery health, and this will help us monitor what sort of systems are getting what level of voltage. Very important for us because we want to make sure that we aren't overpowering things, we aren't destroying things. We want to make sure that everything is regulating at proper temperature, voltages and temperatures. In the bottom, you can see our sort of small snippets of our measurements that we have. And one important one to note is our cell temp, which we will be reading in our battery. It will be very utilized in our next management system, which is our cooling management system. So next slide. And this will be using sort of temperature sensors and to monitor sort of all the sort of areas of our pod, and then also water level, flow rate, and liquid sensors for our liquid cooling. This is because we don't want to leak, we don't want to destroy anything, because our motors will be operating at higher efficiencies and performance when they're cooled properly. We also currently use DC fans for less important, I'm going to say less important things, but things that don't need the stronger level cooling. It's very important that we want to make sure that our system and overall pod is sustainable and will be long lasting, so we don't have to constantly do repairs and fixes, because that can be very costly. And speaking about motors, in our next section, which is by Alex, or other Alex, take it from there.
Yeah, so currently we are using some Bafang B410 motors. They are a little bit on the smaller side, but the reason we picked them is because they integrate nicely with our current pod system. They are essentially hub motors operating at 40 volts DC, and control. Each motor is controlled by a single base runner motor controller, which either receives commands from the onboard microcontroller through a DAC or via tethered controls. So in the future, we are looking at implementing some AC rotary motors, specifically axial flux motors, which compared to standard AC motors, they're essentially, they have a higher power density, higher torque overall, are more power efficient, although they are more expensive. And these actually also have a smaller form factor, which is very useful when operating in confined spaces. Next slide. So sort of related to these, we are also working on some retractable wheel mechanisms, and this is going to be for a future pod iteration. We're using linear actuators and a linkage system, with each actuator outputting about 400 pounds of force. They're controlled through H-bridge controllers operating at 12 volts, and essentially will activate once we're at a high enough speed that we can activate our levitation system and properly levitate. Next slide. And so that brings us to our future goals, which includes levitation as well, via either passive permanent magnet strips or potentially active levitation. We're also planning on integrating a linear induction motor, an inverter system that are running on 3-phase, although this will also require a higher power electrical system with a 400-volt battery bank. And we are also working on our initial concepts of magnetic braking, which will either be electromagnets, which could be stronger than permanent magnets, although we are still planning to have permanent magnets for an emergency system in case we have power loss. So a bit of a safety protocol. Next slide. So that basically brings us to the end of our technical section of this. I would like to thank our sponsors, which primarily the University of Alberta. Next slide. And you can communicate and reach out to us via these links here. Do you guys have any questions?
All right. I think we may be in the clear.